Now, today I want to introduce this topic, workshop tools. But before we go through them one by one in detail, I'll start by mentioning some terms that are important when we discuss measuring systems or measuring instruments. Now, the first term is readability, and this indicates how close the scale of that instrument can be read. For example, when you take your ruler, you have a 15 centimeter ruler and you have a 30 centimeter ruler. Utapata kwamba that 30 centimeter ruler will be read easily. That scale will be read easily as compared to that of a 15 centimeter ruler. So how easily you can be able to read that instrument, the measuring instrument, the scale of that measuring instrument is what we term as readability. Now, least count is the smallest difference between the indications in that scale of that instrument. For example, that ruler, the 30 centimeter ruler, has divisions between those centimeters. Between 0 and 1 centimeter, we have 10 divisions. So the smallest measurement that I can be able to make with a 30 centimeter ruler is 0.1 of a centimeter. That is what we call the least count. The value of the value between the two indications in a scale is what we term as least count. So you'll find that different instruments, the scales of different instruments have different least counts. Kama ya ruler, hizi ruler ambazo tunatumia kwa class ni 0.1 of a centimeter. You'll find that others are 0.01 of a millimeter, depending on the accuracy of the instrument. We have range. Now this represents the least to the largest value that instrument can be able to measure. In our case, this ruler will be able to measure from 0 centimeters to 30 centimeters. So the range is 0 to 30. So you'll find that different measuring instruments can be able to measure different ranges. Now we have sensitivity. This indicates how much the input of a measuring system or an instrument changes when the quantity being measured changes by a given amount. What do I mean? Kwa mfano, I have temperature. I'm measuring temperature. So how much the output of my thermometer will change will be dependent on how the physical quantity that is temperature changes. So essentially the ratio of the output to the input is what we term the sensitivity of an instrument. We have repeatability. Now if I measure a physical quantity over and over again, more than once, and I get the same result, that is what we term repeatability. For example, if I am measuring temperature or if I'm measuring pressure, and then I measure pressure napata ni 50 bars, I measure once, I measure twice or thrice, and I get that my pressure is still 50 bars, then that is what we term as repeatability, and we use repeatability to determine the accuracy of an instrument. You'll find that there are some instruments, when you measure them, the first reading will be, let's say, 50 bars, the second 30, the fourth, the third 60. So you'll see that this, because of certain errors maybe with the instrument or the changes in that measuring environment, then utapata that the output of the instrument will change. That means that instrument is not accurate. Accuracy. Now, accuracy is how close the measured quantity the output of your measuring instrument is to the true value. Now, for example, I have a rectangular workpiece, a piece of metal that is its length is 10 centimeters. I take my measuring instrument, kwa mfano ruler, nikapima nikapata that the length is 10.2 centimeters. So the output of my measuring instrument, how close it is to the true value, which is 10 centimeters, is termed as accuracy. And when we talk about accuracy, then we introduce the concept of error, because we express accuracy in terms of percentage. And for you to get a percentage, then you have to take the value that you get as an output, you subtract it to the true value, and then you divide it by the true value and multiply by 100 to get it in percentage form. So that aspect of error is introduced. So you can find that the output might be greater than the true value or might be less than the true value. Now we have precision. Yeah? You might find that when you take measurements of a physical quantity, then these outputs will be close to each other. Utapata, for example, if I measure temperature once, napata 10 degrees, the next time I get 9.8 degrees, the next time I get 9.9. This means that my instrument is precise. I'm getting the same, the closeness, the groupings of my output is close, they are close to each other. You'll find that an instrument can be precise, but it is not accurate. For example, if I'm measuring temperature, the true value of the temperature is, let's say, 30 degrees Celsius, but the output that I'm getting is 10. But when I take measurements over and over again, I'll get that my measurements are around the same output, 10, 9.8, 9.9. Yeah? So my output is my measuring instrument is precise, but it is not accurate. So the closeness of which the measured quantity are to each other, the output, is what we term as precision. Now we have resolution. Resolution it specifies the smallest change in a physical quantity that is being measured that causes a change in the measurement output. That smallest quantity that will trigger will cause the output to be visible in that measuring instrument is what we term as a resolution. Yeah. So depending on the type of scale, depending on the type of instrument, you'll find that the resolution of these instruments differ. Now we have threshold. If I was to increase the physical property that I'm measuring, kama temperature, gradually from zero, you'll find that the input will have to reach, that physical quantity will have to reach a certain minimum level before that change in that input or that physical quantity can be registered by the measuring instrument, so that we can get an output, or the output is large enough to be detectable. So that minimum level of the input of that physical quantity is what we term as threshold. So different measuring instruments have different thresholds. We have another term known as response time. Now, once I change, once the physical property that I'm measuring, for example, temperature changes, the time it takes from that time that physical property changes up to the point that an output is registered on the measuring instrument or the measuring system is what we term as response time. So you'll find that there are some instruments that are quick to register that change, and there are some instruments that will take some time because it's on a lag. They will take some time before they can be able to register that change, and that time is what we call response time. Now we have a term known as tolerance, and the best way to explain this is, for example, you want to buy a nut and a screw, a bolt and a nut. Utaenda kwa hardware moja ununue nut ya 10 millimeters diameter, you go to another hardware and buy the bolt for 10 millimeters hardware. Yeah, despite buying these two bolts and nuts at different places, you'll find that these two components will fit together, and that the reason is because these components have that aspect of tolerance. Kuna hiyo aspect of tolerance when they have been when machining that product. Even you as an engineer or a technician or whichever job that you'll be doing, fundi wa nguo wa kiatu, you have to ensure that when you're making something, you have to give that measurement or that kitu ambao unapima an allowance. You have to give it an allowance. You do not cut kama ni chuma. Specifically, if I want 10 centimeters, I won't cut 10 centimeters. I cut like 10.5 so that I'm able to have an allowance in case there is something I need to change. If I need to file, I'll be able to file mpaka nifike 10 centimeters. If I cut exactly 10 centimeters and let's say my edges are rough and I want to file, when I file utapata kwamba that length will decrease, itafika 9 centimeters. So by introducing the tolerance, then we are able to give our measurements an allowance just in case we need to fix some errors. So tolerance is that allowable amount by which a measurement can vary. So if I'm making a measurement, unapatanga sana sana, we say that my length is 100 centimeters plus or minus 0.2 of a millimeter, or 0 plus or minus 0.1 of a centimeter, and so on and so forth. So that allowable amount that measurement can vary is what we term as tolerance. Now, when I say plus or minus, it means that there is a maximum limit that tolerance can go to, and you also have a minimum limit that tolerance can go to. Now, this maximum and minimum permissible, or those extreme measurements in which that actual size is contained. That one, if my measurement is, my actual measurement is 100 centimeters, and I say that plus or minus 2 centimeters. So my maximum limit is on 1 or 2 centimeters. My minimum limit is 98 centimeters. Okay? So those two extreme ends of the measurement in which the actual measurement is contained are known as limits. This is what we term as limits. Now, scales. You'll find that different measuring instruments will have either a linear scale or a non-linear scale. When we talk about linear scales, these are scales whose divisions or sections or proportions are equal in size or are equal in value. For example, the ruler that we use in class, the 30 centimeter ruler, you'll find that the divisions, one division is equal to 0.1 of a centimeter. It is 1 millimeter. So if so that 1 millimeter will increase from 0 equally up to 30 centimeters. So that is what we call a linear scale. But there are some instruments like a moving iron measuring instrument that is used to measure current. It can be an ammeter, or it can be a voltmeter. You'll find that these type of instruments do not have a linear scale. They have a non-linear scale, meaning that those divisions are unequal in value. They are not constant. So you'll find that, for example, that moving iron, the beginning from 0, utapata that the groupings of those divisions are so close together. But as that scale increases in size, then those groupings also increase in size. So that is a non-linear scale. Now we have limits and fits. Yeah, we have limits and fits. Now, when we talk about limit, is what we have mentioned just before. Yeah, those two extreme permissible sizes, yeah, in which the actual size is contained. When I say that my actual size is 100 centimeters plus or minus 2 centimeters, so the limits, that 102 and 98 are what we term as limits. Now, fits in engineering, fits are usually refer to the clearance between two mating parts. If I have a male part and a female part and I join them together, the clearance between those two mating parts is what is known as fits. Now, depending on how I want the movement between those two mating parts, then we can classify fits according to 3 major categories. We have clearance fit, we have transition fit, and we have an interference fit. Now, the best way to explain this is by having a hole and a shaft. In this case, what I want to mate is a hole and a shaft. So for a clearance fit, you'll find that the diameter of the hole is larger than the diameter of the shaft. So the shaft can easily enter the hole. That is what we term as a clearance fit. For an interference fit, the diameter of the shaft will be larger than the diameter of the hole. So I will have to apply some force, some lubrication, or I can either hit the shaft or the hole to increase or decrease the diameter so that those two parts can be able to mate together. Yeah. So for the interference fit, the fit is tight, so it doesn't allow any movement. But for the clearance fit, since one of the parts is larger than the other, then so they are able to move relative to each other. Yeah. So these terms that are here are included in the notes that I have sent in the Google Classroom. You'll be able to find for each class. I've sent these notes. So go through those notes and see what these terms mean in reference to fits. These terms are in fits. Kwa sababu you'll find that one of the most important things ni hii line ambayo nimechora hapa. This line is known as the zero line or the line of zero deviation. When you're making a design, mmepatana with your designers, you yourself are participating in the design of a part. That measurement, that size of that component that you're designing is what we call the nominal design, the basic size of that part. If it is a pipe that we want to design, that in our design, in our calculation, that part will be is supposed to be 10 centimeters. But when you actually come to machine that part, you have to include the tolerance, the aspect of tolerance, so that when you are making those parts, you'll find that kuna ile allowance for any errors, for expansion, for contraction. So you have to include that allowance. So when you have a basic size that you get from the design and you have the tolerance, then we come up with, we find other terms like deviation, we have tolerance, we have upper deviation, lower deviation. So go look at those notes, find out what this term mean when it comes to fits. Now, I want to mention I want to talk about those terms. Yeah, so go look at them and find out what they mean when we talk about fits. Tuko pamoja mpaka hapo? Oh shit. Hello. Nilipotea na hakuna mtu ananiambia nimepotea. Nilipotea na hakuna mtu aliniambia nimepotea. Nimekuwa nikiongea peke yangu bana.
Tulisema.
Unani text kwa ama unaniambia class rep ani text. Unajua nilikuwa nimesonga. Nilikuwa nimefika wapi? Ama siku hata nimeanza.
Hebu rudisha hiyo
kidogo tu. Unajua na assume tuko pamoja, kumbe nilipotea. Nilikuwa nisha mention these terms. Nilikuwa nimefika wapi?
ulikuwa mahali hapo ya tolerance.
Had I mentioned about this diagram? Ama hatukuwa tumefika kwa hii diagram?
Hapana.
Okay.
Tulikuwa kwa tolerance hapo mwisho.
Okay. Now I was saying, when we measure, when we make a measurement, you'll find that we have that allowance in the measurements that we make. That allowance enables us to be able to fix any errors that we get. Kwa mfano, if I want to cut a 10 centimeter piece of metal, I will not cut exactly 10 centimeters. I will cut 10.5 centimeters. So in case I want to machine, or in case I want to file, ama nataka kufanya processes, then when I file, for example, then I can be able to get the exact 10 centimeters. So that allowable amount by which a measurement can vary is what we term as a tolerance. Now, when I say plus or minus 0.2, unapata that we have a maximum and a minimum limit. The maximum limit being that 1 or 2. If my measurement is 100 and I say it's 100 plus or minus 2 centimeters, then the upper limit will be 1 or 2 and the lower limit will be 98 centimeters. Yeah, so that maximum permissible, those two extreme permissible measurements in which the actual 100 centimeters is contained is what we term as limits. This is what we call limits. Now, scales. scales can be linear or non-linear. When I talk about a linear scale, you'll find that this is a scale whose divisions or markings are equally spaced, meaning that the value of those divisions is equal. It is equal in size. And a very good example is the ruler that we use in class, the 30 centimeter or the 15 centimeter ruler. Those divisions are 1 millimeter or 0.1 of a centimeter in size. So when I go from 0 to 30, I'm increasing linearly with a millimeter. My scale is increasing linearly by a millimeter. So that is a linear scale. But you'll find instruments that do have a non-linear scale. For example, moving coil instrument. Moving coil instruments are used as ammeters or voltmeters. You find that the scale on those instruments do not have are not linear. The divisions are not equally spaced, meaning that those divisions are not equal in size. Yeah. So you come here, moving coil instruments, you'll find that the beginning of that scale from 0, those groupings are so close together. But as you increase in size, then the instrument also increases. I mean, the scale also increases, or the divisions of that scale also increase in size. Now, limits, we've just mentioned what limits are. Those two extreme permissible measurements in which the actual size of that measurement is contained is what we term as limits. So if my actual measurement is 100 centimeters, so when I say plus or minus 2 centimeters, so the upper limit or the maximum limit will be 102, and the minimum or the lower limit will be 98 centimeters. Now, when we talk about fits in engineering, fits refer to the clearance between mating parts, parts that can be joined together. So when you talk about mating parts, we have the male part and we have a female part. For example, a screw and a nut. The nut is the male part and the screw, no, the nut is the female part and the screw is the male part. Now, you'll find that in fits, when you talk about the fits, depending on how I want the motion to be between those two mating parts, then I can have different categories of fits. And the major categories of fits, we have a clearance fit, we have a transition fit, and we have an interference fit. Now, when we talk about a clearance fit, the best example I can use is this over here. We have a hole and we have the shaft. Now, when we talk about clearance fit, the diameter of the hole is larger than the diameter of the shaft. Yeah, so the shaft can easily enter and leave the hole. So there is a relative movement between those components, the hole and the shaft. Yeah, so we can be able to assemble these parts easily, allowing since there is space between them, there is that it allows for the rotational movement or the movement between the relative movement between those two parts. But for an interference fit, you'll find that the diameter of the shaft will be larger. The diameter of the shaft will be larger than that of the hole. So I will have to induce some force or lubrication, or I can heat those two components to either decrease or increase the diameter of either the shaft or the hole, so that these parts can be able to fit together, to mate together. Now, these interference fits are necessary if I want to have a tight fit, if I do not want to have two parts that are moving. That is what we term as an interference fit. Now, a transitional fit encompasses those two. It can be either. So the shaft may be a little bigger than the hole, just by a bit, requiring some force to create that fit. Or on the other hand, it can be a clearance fit, such that the shaft diameter is a bit bigger than the hole diameter is a bit bigger than the shaft, so it can easily enter, becoming a clearance fit. So when you have a fit that can be either can be in between the clearance and the interference, then that type of fit is known as a transitional fit. Now, these terms are necessary when you talk about fits, and I've sent them in the notes Pale Google Classroom for both classes. Yeah, so you'll find these terms and what they refer to when we talk about fits. But something that I want to mention, a very important term, ni line upper. This line is known as the zero line or the line of zero deviation. And this is usually used to denote that basic size, the size that when you that of a component or a measurement that you come up during a design process. For example, we want to design a pipe, and we say that the diameter during our calculations to kapata that the diameter of our pipe will be 10 centimeters. So that is what we term as the nominal diameter or the basic size of that pipe. But when you're machining that pipe, or when you're after during the production process, then you have to cater for tolerance. You have to include those allowable measurements to be able to accommodate future for mfano expansion and contraction of your pipe, or to be able to accommodate for errors. Yeah? So that is when we introduce tolerance. Yeah? So that basic size is the most important, or it's known as the zero line of deviation. Now from that zero line of deviation, then we come up with other terms like lower deviation, upper deviation for the shaft. We have lower deviation and upper deviation for the hole, and so on and so forth. Yeah, so these terms have already been specified and what they mean in those notes. So go through them, understand them. You can write them down in your notes so that you can be able to know what they mean. Are we together? Come out to pamoja, please, and mute and say that I'm present, so that I can know if we are in the same class. We are together?
Yeah.
Okay. Now, today's main topic is marking out. I wanted to introduce this topic, marking out, and what marking out refers to is the transfer of a design onto a workpiece. When I want to draw a design, when I want to draw a line on a piece of metal, if I want to draw a circle on a piece of metal, that process is known as marking out. Yeah. And what is the purpose of marking out? The first purpose is to indicate the workpiece outline. The places where we have holes, slopes. Yeah? Remember, not all workpieces will have a regular shape. Remember, we looked at castings. Kama unafanya casting, you solidify your metal, you'll find that those pieces of metal will have awkward shapes. The shape will be irregular. So for you to be able to outline the shape of that workpiece, then you can mark out draw an outline on the surface of that workpiece. You can also use the second purpose of marking out is to provide a guide when setting up that workpiece on a machine. For example, I want to put my cylindrical pipe onto the lathe machine, and I think I've shown videos of lathe machines, so we have an idea what a lathe machine is. Now I want to put that workpiece onto a lathe machine. I will draw a point on that circular pipe, such that when I put that pipe into the lathe machine, nitajua this is the point inafaa kufika hapo. That is the point at which, let's say if I'm cutting, I should not go beyond that point. So I'm providing a guide when setting that workpiece onto a machine. So those are the two major purposes of the process of marking out. Now, a datum. A datum is a very important term, or a very important concept when we talk about marking out. And this refers to the reference point. The reference point from which we will be able to take all our dimensions. For example, katika your notebook, when you draw lines onto that on your notebook, or when you're drawing lines during technical drawing, usually let's say you draw from the edge of that paper. That edge is what we refer to as the datum, that reference point from which you're taking your dimensions. So a datum, depending on the shape of a workpiece, can be a point. This is what we refer to a datum point, because in this case we're taking dimensions that are circular in nature. When I'm taking dimensions that are circular in nature, or if I want to draw an arc or a circle, then I will have to have a datum point, a point. If I want to make dimensions, for example, in engineering drawing, maybe uchore such a component. Then when I make measurements from an edge, for example, this is the edge or the outline of my drawing, then that is what we term as the datum edge. A datum edge can also be a center line. Remember, when you're drawing when you do your engineering drawing, there are times that you make measurements from this center edge. The distance from this point to this point. Let's say this is a crank shaft or an arm. When I take the dimensions from this point to this point, then I've used those two center lines as my datum point. So this is So depending on the shape of your workpiece, then we can be able to identify different reference points. So it can be an edge, it can be a center line, or it can be a point. Now, what are some of the instruments that we use, or some of the equipment that we use to draw lines or use to transfer designs onto our workpiece? The first and the most important one is a surface table. Now, a surface table is one whose it's usually made from cast iron, but we have some that are made of granite and other materials. But the common one that you'll find in the workshop is usually made from cast iron. Now, it is usually used to check the trueness of the flat surface of your workpiece. Reason being is because this table has been machined accurately. Its squareness and parallelism is accurate, such that from this edge to this edge, ni flat. It is completely flat. Hakuna milima na mabonde kabisa. That surface is purely flat. So when I place a workpiece on this table and I want to be able to draw a reference edge or a datum on my workpiece, then it is possible, because this reference surface will be able to test the trueness of the flat surface of my workpiece. Then it is possible to establish a datum from which I can be able to take my measurements on my workpiece. So this is a surface table. Now, if I'm going to be making if I have a smaller workpiece that is smaller in size, then I do not need a surface table. I can use a surface plate. It is a surface plate still made of cast iron, but it is used it is used on smaller workpieces. Now, these surface plates and surface tables are usually machined to different levels of accuracy. Yeah, so you can find that kuna grade A of a surface table, we have grade B. So you'll find that the accuracy of grade A is kama 0.005 millimeters, grade B is 0.02 millimeters, and so on and so forth. Yeah. Now, how do I use this table? I have to apply a thin coat of oil. You apply a thin coat of oil, you spread it evenly on the surface. Yeah. You clean your workpiece, place it on the plate or on that table, and you move that workpiece along the parts. I mean, you move it along the table. So since you have applied a paste, you have applied an oil with a red paste on the surface of this table. So you'll find that if my workpiece is flat, then the whole of that face will be covered with that paint or that paste. If it is not flat, then some parts of that workpiece will have the red paint, and some parts will not have. So meaning that workpiece is not purely square. It is not square kabisa. So it tests the trueness of the flat surface of our workpiece, and then once we have tested the trueness of the surface, then we can be able to establish a datum on our workpiece. Now, I can use some other tools known as parallels. If I want to raise my workpiece a certain height from the reference surface or the reference table, then what I need or what I use are parallels. They are flat in nature, such they are machines. They are precise in the sense that their squareness and their accuracy ensures them that they are flat in nature. They are parallel to that surface. So when I put a workpiece on top of the reference table, then that workpiece still maintains the parallelism with the reference table or the reference surface, so that I'm able to create, for example, a datum on this edge, but I'm creating that datum on the reference surface, but I've raised my workpiece a certain height. Yeah, so depending on the size of my workpiece, then I can be able to have parallels of different dimensions, and they usually come in pairs. Haikujangi ikiwa moja inakuja, they come in pairs. Now, a jack and a wedge. If I have a workpiece that has an irregular shape, an awkward shape, for example, a casting and a forging, and I want to establish a datum on that workpiece, then it is essential for me to use these jacks and wedges to ensure that these workpieces do not azicheza-chezi, when I'm trying to get my reference edges. The same way when you're fixing a car, mnaonanga ma mechanics wakifanya repairs, they put mawe nyuma ya tire so that the car does not move to and fro. Even though you have engaged the handbrake, they still put that as a precaution so that the car does not roll off. Mtu anaweza sahau akatoa ile handbrake ama hakuiweka, so when the mechanic is underneath the car inasonga. So the same concept, you put a wedge or a jack to support that workpiece, that irregular shaped workpiece, to prevent it from rocking to and fro, and to ensure that it is parallel relative to that reference surface. Then we employ the use of jacks and wedges. Now we have another tool known as an angle plate. Now if I want to place my workpiece 90 degrees to the surface, I want to place 90 degrees to the surface of the reference table. Let's say this is the reference surface table, and I want to make an inscription, I want to draw a line, but I want my workpiece to be 90 degrees to that table. What I use is an angle plate. As you can see, this angle plate, it is made from cast iron, and these two faces have been machined. These two faces have been machined square and parallel to each other, but they are machined to be absolutely 90 degrees. It is known as an angle plate, so it is 90 degrees. Now, what these slots are for is they provide a place for this workpiece to be clamped. Unaweza shikilia this workpiece by using clamps which are put through these slots. So I can put a clamp between two slots, nishikilia my workpiece, and it will be 90 degrees to my reference table. So I can be able to make markings on that angle plate. And this is the diagram here that shows what I am saying. We have a sheet metal, and I want to make markings using this tool over here. This is known as a surface plate. What I do is I will take this piece of metal, place it next or on the face of my cast iron angle plate. Then using a clamp, I will hold, I will secure this workpiece, and it will be 90 degrees to the reference surface. So I can be able to make inscriptions, diagrams, lines or circles or whatever on the face of this sheet metal. That is what we use an angle plate for. Now we have something else known as a V-block. Now a V-block is used to secure circular workpieces or workpieces that are round in nature. So V-blocks that are large, there can be V-blocks that are large as a car, or even bigger. Those are usually made from cast iron, but hizi ndogo ndogo are usually made from hardened steel. And they usually come with a clamp. They come as a pair. Kuna clamp na kuna the V-block. So this clamp is known as a U-clamp. It's what you secure by tightening this bolt. It secures that workpiece on that V-block. So if I want to make an inscription onto the surface of that circular workpiece, then I can do so by securing it on the V-block. Now the faces of this V-block are machined to a high degree of accuracy, of flatness, squareness and parallelism. As you can see, hizi faces ziko square vizuri sana. They are flat. They are very accurate, such that this V, this 90 degree V, is at the center of these faces or the edges. They have been machined to a great sense of accuracy that this V, this 90 degree, is at the center of these faces. Are we together?
Yes.
Now, another tool that we use is an engineer square. And this is a very important tool, and I think we saw it when we were looking at the videos making threads, especially the internal threads. Now we use this engineer square for setting the workpiece square to the square to the reference surface. We have this which is known as a stock. We have this part which is known as a stock, and we have the blade. Yeah. So the stock is usually made from bronze, and the blade is made from hardened steel. and it is ground, it is machined to give the edges a high degree of accuracy in terms of straightness, parallelism, and squareness, such that if I want to draw lines that are perpendicular, to a workpiece, for example, this one, what do? I will place this stock on the reference edge or the datum of my workpiece, and since it is made in such a way that the blade and the stock are 90 degrees to each other, then I'm able to draw a perpendicular line onto the workpiece. Remember, I can be able to draw a line using a ruler. I can draw a line on that workpiece, but inaweza teleza mkono, then the angle changes. I'll have a line, yes, that is straight, but it will not be 90 degrees. So if I want to make 90 degrees lines or perpendicular lines from the reference edge, so what I use is an engineer square or a tri-square. Now, it can also be used to test the squareness of the workpiece. Now, what do I mean by this? Remember, when we are watching those videos and I want to drill using a vertical drill, my workpiece. This is my vertical drill. This is my workpiece. So I have to ensure that this drill haichezachezi, whether I'm doing it manually or using a machine. Ile machine is easier kwa sababu it has been set in place. But if I'm doing it by hand, I have to ensure that my workpiece, my drill, is drilling perpendicularly to my workpiece. So what do? When I'm drilling, when I'm setting that point or a drill, then I have to keep on ensuring that that drill is 90 degrees to that surface. So as I drill, I'll put my or when I'm making internal threads manually, then I'll put my engineer square next to that tap or that drill bit, so that it is drilling perpendicular to that workpiece. So we are testing the squareness of that drill, or we can be able to draw perpendicular lines on the workpiece. So that is what we use an engineer square for. Now we have another interesting tool that is known as a combination set. Yeah. Now this combination set incorporates a tri-square, it incorporates a protractor, and it incorporates a spirit level and something known as a center head. So this combination set has three heads. We have the square head, we have the we have the protractor head, and we have the center head. Now this, I'll start with the protractor head. If I want to make lines, I want to scribe lines that are at an angle. This is my workpiece, and I want to draw a line that is at an angle. What will I do? I will set that angle on this protractor. It has those calibration from 0 to 180 degrees as a normal protractor. So depending with the angle I want, then I will set this protractor to that angle. Then I will place my workpiece on this edge. So nitaleta hii kichwa on this edge, along this line, this edge of that protractor head. Then using this tilde rule, then I can be able to make my inscription, I can be able to scribe a line on that workpiece. So we use that to scribe lines at an angle of the workpiece. Now the square head. The square head will do the same work as this tri-square. The only difference is that this square head will not be as accurate as this tri-square. Look at this tri-square. It is fixed. This stock and the blade are fixed in place. But these heads, the square head, the protractor, and the center head, are movable. They have slots that allow them to move or slide along this tilde rule. So this, if not secured tightly, then it itacheza, meaning that this side is what, as you can see, each side inakaa kama an engineer square. We have an angle here that is 90 degrees. So we use this edge to draw lines that are perpendicular to the workpiece. This edge, we use it to draw lines that are 45 degrees. This is a 45 degree angle to the steel rule. Now, since this is a movable head, then we incorporate something known as a spirit level. I don't know whether we've been able to see a spirit level, we have seen it before, but it is a tube that has a liquid inside and a bubble. So when that bubble is at the center of that tube, then that indicates that instrument is accurate. So since it is a movable, we incorporate a spirit level. Now this center head is used to determine the center of circular workpieces. Yeah? So if I want to determine the center of a pipe, I will put a pipe apple, and this blade, the steel rule, will pass through the center of this V. When it passes through the center of that B, then I can be able to mark out the center of that circular workpiece. I can be able to determine the center of that workpiece. So we have a protractor head, we have a square head, and we have a center head. So it is a 3-in-1 combination. Now we have a scriber. We've been talking about drawing lines on the workpiece, and this is the tool that we use to draw those lines. Yeah, it is usually a piece of hardened steel that has a sharp point at the end. It is a hardened steel that has a sharp point on the end. Now we have this which is known as a pocket scriber, and we have this which is the common one that you'll find in the workshops. This one is the common one because it has a bent edge. We have a straight edge and we have a bent edge. Now this bent end is used to scribe places that this straight end cannot be able to reach. For example, if I want to scribe corners or inside grooves, and this straight edge cannot be able to find, cannot be able to reach those points, then I use this. For example, I have a workpiece ambayo iko na shimo, and I want to scribe the upper part of this edge, and I want it to be a straight line. I cannot be able to use this straight end, so I'll use this curved end and nitaingiza katika this workpiece, and you'll find that since it is bent, then it is able to draw lines at places that this straight end cannot reach. Now these ends, the sharpened ends, are chamfered. When I mean by chamfered, ziko rough per se, so that they do not burn. Remember, when you're scribing, you are producing heat. You are essentially ni kama una scratch, so you have to ensure that those ends do not burn because of the heat, so you chamfer them. And also they have to be kept, they have to be sharp. You have to make sure that they are maintained as sharp, to make sure that when you're scribing lines on the workpiece, then they give you well-defined lines. The same way when you're doing your engineering drawing, you have to sharpen your pencils so that you can get well-defined lines. It's the same thing when you have to ensure that those scribers are sharpened. They have sharp edges. Okay, now we have something else known as a surface gauge. Now this incorporates a scale that is vertical in nature and a scriber. This it can be a scale ama inaweza kuwa ya sio scale. It can be just a vertical stand, but it can have a scale ama itakuwa na scale and a scriber. Now what do we use this surface gauge for? If I want to make markings on a workpiece that is parallel to the reference surface, kwa mfano, this is my reference surface and my workpiece is a bit higher. It is not on the surface, iko mali imeshikiliwa na instrument ama equipment it is at a point parallel to the workpiece. Now what do I do? This being my reference surface, I will place this tool at a point, and this is my workpiece. Kwa mfano, I have a circular pipe ambayo imeshikiliwa na lathe machine. Let's say this is my lathe machine, and I have my workpiece secured on the lathe machine. Then I will put this surface gauge at just the height of my scriber, so that it touches my workpiece. So when I rotate this workpiece by hand, then you'll find that we'll have a line that is inscribed around that surface gauge. It is easier than just unsecuring ama removing the workpiece from the lathe machine, niweke chini, nichore laini. We use a surface gauge for that purpose of making lines ama scribing workpieces that are parallel to the reference surface. Now, the accuracy of this surface gauge is not that good, kwa sababu it depends on how secure this scriber is. So if I don't tighten this screw vizuri, then hii scriber itakuwa inacheza cheza. So if I place this scriber on the workpiece and I rotate this workpiece, you'll find that this scriber will be itakuwa ikicheza cheza. Also, this bases, the base of this surface gauge, if it is not secured properly, then it will move. That surface gauge will move So the accuracy depends on how well the technician is when using that tool. So that is the purpose of a service gauge. Now we have dividers and trammels. We have all interacted with dividers in our classes. Ni ile tu ambayo unapata kwa set. Now what do we use a divider for? We use a divider, for example, if you want to transfer dimensions from a scale to the workpiece. So I will interpanua my divider, measure 5 centimeters on my ruler, for example, and then I can be able to mark that 5 centimeters onto my workpiece. So I can be able to transfer measurements from a scale or a scale to the workpiece. I can also be able to measure a point, 2 points on the workpiece accurately on the scale. So I will put these legs, nitapanua hii miguu ya hii divider, place those 2 legs on the 2 points I want to measure, then I can transfer or I can put that distance onto the scale so that I can be able to identify the measurement between those 2 points. Then I can also use these to draw lines, to draw circles and arcs. So if I have a point datum, for example, this is my point, then I can place one leg at that point, and using the other leg, then I can be able to draw a circle or an arc. So I can use a divider to do that. Now, this divider is of 2 types. We have a spring ama screw type divider ambayo tunaona hapa. There is a screw here and a nut, such that the opening and closing is I can be able to open the divider by loosening this screw or tightening it to close it. We have the usual one, the normal ones that we have in our sets. We only have a fulcrum, and using our hands, the force applied using our hands, then we can be able to open or close the divider. Now, the limitation of this divider is the size that I can be able to draw the circle. You find that the maximum diameter of most dividers is 150 millimeters. Now, if I want to make the circles or arcs that are of larger size, then I use something known as a trammel. A trammel is a beam that has divisions or a scale, and we have these scribing tools, these scribing points that are movable. So if I want to draw a circle or an arc that is 500 millimeters in diameter, then I can be able to kama hii, I fix this one in place and then move this one mpaka mahali I can get a radius or a diameter of 500 millimeters, and I can, using a fixed datum, let's say this is my fixed datum, then I can be able to rotate this trammel and get a circle whose diameter is 500 millimeters. So when we are making circles that are larger in size, what we use is a trammel. You will find this in woodworks, you will find this in metalwork. It is a very important tool because this has a limitation of size. When you bend this beyond a certain point, this pivot or this fulcrum will break. So we use this, a beam that has dimensions, has divisions or a scale, and we have scribing points. We have scribing points that can be moved. Kama ya woodwork utapata, this one of these scribing points is a pencil. We can be able to attach a pencil there, and then you can be able to make circles or arcs of larger dimensions. Are we together? If you're together, please unmute and say that I'm present. Philip, Omondi, Rahma, tuko pamoja. Sawa. Yeah, so let's continue. We have another tool known as a vernier height gauge. Now, it does the same job as this surface gauge, but now, if I want to obtain a higher accuracy, we have what we use is a vernier height gauge. Now, as you can see in a vernier, and I've sent a video in the Google Classroom that will show you how. I want you to go through that video very carefully so that you are able to interpret how to use a vernier scale. Kwa sababu a vernier caliper and a vernier height gauge both have a vernier scale. We have the main scale on this vertical shaft, and we have this movable vernier scale that slides along the main scale. So go find out how, from that video, how to read a vernier height gauge. So the accuracy of this is improved because we have introduced the vernier scale. Now, this vernier scale carries a jaw upon which you can be able to put various attachments. This is a chisel. So when I'm marking out, I'll use a chisel. So I will clamp, I'll put a jaw on this chisel, and then depending on the height, depending on the measurement I want to inscribe on the workpiece that is parallel to the reference surface, then I'll move, let's say I want to measure 15.1 to 15.12 centimeters. So I want 15 centimeters and 0.12 of a centimeter. With that surface gauge, I cannot be able to do that because you'll find that maybe on that scale, we'll only have the main scale kama ile ya ruler 0, 1, 2, 3, 4, 5, 6. So by introducing this vernier scale, then we can be able to make measurements of that point something of a millimeter. So then by attaching a chisel on that jaw, then I can move this, measure 15 centimeters on the main scale and measure that point something of a centimeter on the vernier scale, and that will, then I can mark using the jaw, the chisel, to obtain an accurate or more precise marking on my workpiece. Now we have a precision steel rule. That is the ile ruler ambayo it's just a normal ruler, but now it's made of steel, and we use this for general measurements. If I want to measure the length of a piece of metal, I'll just use a steel rule. So it is made from hardened steel, and both sides are machined to be flat, and then on one side we have graduations, markings in terms of inches, as you can see on this side, and then we have millimeters and centimeters on the other side. So we use it for general measurements in the workshop. Now we have something known as a center punch. Now this center punch is used to provide the center location for dividers and trammels when scribing circles. Remember, let's say when you're drawing when you're doing an engineering drawing, a technical drawing, and you want to draw a circle, you have to identify where you're going to place your datum point, where you're going to place your divider, your compass. In marking out, remember when you're using a divider, you are marking out a piece of metal. So for you to identify that center location, you use a center punch. This center punch is usually this edge of the center punch is chamfered. It is at an angle. It is chamfered, as you can see. It is not smooth, and then we have it is iko na angle hapo mbele. So depending on the type of angle, then we have different types of punches. We have a center punch, we have a dot punch. So that included angle can be 90 or 60 degrees, and it is chamfered to prevent from burning. And the body is nulled, imechongwa, so that you can be able to grip it by hand. So we tunashika this part with our hand, and then we place it where you want the center of our circles to be, and then we hit this edge, the head, with a hammer, and this point will be inscribed by a point. A point will be inscribed by the edge, that sharp edge of the punch. Now we can also use these two to identify the center, the start point of drilling. If I want to start drilling a point on a workpiece, I don't start drilling immediately, especially if I am not experienced. So what I'll do is I'll use a center punch, hit that point on the workpiece, kwa mfano hapa, and say this is where I want my drilling to start. So then I can be able to position my drill at that point, and since kuna a dent, then my drill will be able to pick that dent and continue drilling from that point. I can also use this center punch to permanently mark the position of a scribed line on a workpiece. For example, this is my workpiece, na nimescribe a line, nimechora line using my scriber on that workpiece. To ensure that this line is visible permanently, then I will intergongelea center points on this line to permanently show that the position of that line by punching a row of center dots. Sawa sawa. So depending on the type of angle, the included angle, then we can have other types of punches. We have dot punch. A dot punch is a smaller center punch. They're usually made from steel, hardened steel. Now we have clamps, as we had seen in that picture of an angle plate. We can have different ways of securing the workpiece onto other equipment, and we use clamps. These clamps ensure that your workpiece is secured. For example, when we looked at that video, making threads on a pipe, we saw that technician ama that engineer alichukua ile pipe vice yake akaiclamp on the table so that vice does not move when he secures his pipe. So we use these clamps to secure workpieces or other equipment onto other equipment. Now we have these we have so many types of clamps. We have the U clamp that we saw, on a V block, but we have these are the most common ones that you will see in the workshop. We have a G clamp because it resembles the letter G, and we have a tool maker's clamp. So these are used to secure the workpiece on top or over, to secure the workpiece over another piece of equipment. Now we have calipers, and calipers can be of two types. We have the inside and the outside calipers. Now outside calipers are used to measure the external dimensions of, for example, around workpiece. Kwa mfano a pipe. If I want to take the external diameter of a pipe, I will take my outside calipers and place one leg on that side and one leg on the other side, and then I will be able to transfer these dimensions onto a scale and determine the size of the external diameter. And I want you to note, the outside calipers, their legs are facing inward. Their legs are facing inward. For inside calipers, their legs are facing outward. Why? Because I want to make I want to determine the internal dimensions of, for example, a pipe. Now, if I want to determine the internal diameter of this pipe, I cannot use outside calipers because the outside calipers meno yake ina face ndani. So when I put these calipers on the inside, they will not be able to make the dimensions. I'm gonna take the dimensions. But the inside calipers, utapata meno yake will be able to touch that surface of the internal diameter. Then I can be able to determine the internal diameter. Nitapanua miguu yake, touch one leg on the one side of that pipe, and then touch the other leg on the other side of the pipe, and then transfer these measurements onto a scale, and I'll be able to determine the measurement of my internal diameter of a circular workpiece. Now, as you can see, these calipers are of two types. We have the ordinary type, and we have the spring type, ama the screw type. By loosening and tightening this, then I can be able to open or close these legs for the screw type. For the ordinary type, the legs are only supported by a pivot, a fulcrum. So by using the force, by employing force by using our hands, then we can be able to open or close those calipers. Now we have other calipers known as hermaphrodite calipers. Let me see. Mpaka hapo tuko pamoja. Now we have hermaphrodite calipers. I'm trying to look for an image. Kama ilipotea. These are known as hermaphrodite calipers, also known as odd leg or Jenny calipers. Reason being is that we have one leg that is straight, and we have another leg that is bent. Now, what do we use these calipers for? If I want to draw a line that is parallel to the reference edge, for example, I want to draw a line or inscribe a line that is, let's say, 5 centimeters from the reference edge. What I will do is I'll go take these hermaphrodite calipers, then measure 5 centimeters between those two legs. With a straight edge, I will place it on this reference point. This is my datum. So I will move it along this straight end as you can see, there's a provision for it to be able to move along that reference edge. That straight end, that straight leg hapo mwisho imekuwa curved, ama there is a slot. So when you attach it to that straight, the reference edge, then I can be able to move this hermaphrodite caliper along that straight edge, and this sharpened end with the scribing, with the scriber, will be able to mark a line that is parallel to the workpiece. We use that for marking parallel lines to the workpiece. Are we together? Now that is what we use a hermaphrodite caliper for. Now today I wanted to reach there, but from the notes that I have sent, you will find the techniques of marking out. What is the method of marking out a workpiece? I want you to read that, because I will not cover it in class. And even I've given examples of marking out different types of workpieces. One that is rectangular, has a regular shape, a regular rectangular shape. One that has holes. So you can see the different methods of marking out the different shapes of workpieces. So go through them, go through the notes that I've sent, so that when you meet next time, we are going to now go through the other hand tools that we find in the workshop, like files, chisels, hammers, and how to use them and how to take care of them. Sawa sawa.